Okay, so what we're going to cover today is log functions. Okay. Um, yeah, we'll cover the definitions and some log rules, how you could work with them, stuff like that. All right, cool. So the first thing we want to define, oopsies. First thing we want to define very loosely, this will be definition 13, is the form of a log function. Okay, so log functions are typically of the form log A, sorry, log base B of A. Okay, what does this mean? What does this mean? Oh, and let's say it equals to some C. Okay, all this means is A is equal to B to the power of C. That's it. So for example, log base 10 of 100 is equal to 2 because 10 squared is equal to 100. Another example is log base 3 of 81, which we can write as log base 3 of 9 squared, right? Because 81 is 9 squared. But we know 9 is equal to 3 squared, so it'll be log base 3 of 3 squared, right? Because we're breaking this 9 into this 3 squared, which is going to give you log base 3 of 3 to the fourth. We're not adding, okay? We're multiplying. 2 times 2 is 4, okay? And that is going to give you 4 because 3 to the power of 4 is 81. Easy, right? Some interesting notes. First, log functions are inverses of exponential function. Okay. And once you get the hang of this, and you get the hang of this, all of their log rules start to make a lot of sense. Okay. So let's talk about some properties. One, oh, one more thing. Log base e of some x is going to be the same as ln of x. Okay. That's the shorthand. And for our purposes, we'll almost exclusively be using log base e. So I will almost always be using ln. So the first law will say ln of a times b is equal to ln of a plus ln of b, right? Because what you're doing is you're saying e to what exponent, like k, is equal to a, right? And e to some exponent j is equal to b. So naturally, right, e to the, or ln of a times b is going to capture these two exponents additively, okay? Because e to the k times e to the j, e to the k plus j. Okay. The next thing we'll cover after I erase all this is ln of a divided by b. Okay. 2 ln of a over b is ln of a minus ln of b. Same reason. Um, and what you can note is um, a divided by b, if you write it in the same exponent base, so like b to some power of uh, j divided by b to some power k, right? Little b, right? It's going to be b to the j minus k. And so if you take log base e of a, you capture j, and then you do that with b, then you're going to get j minus k. Alternatively, you can divide first, that gives you j minus k. You take the log of that, and that still spits out j minus k. Okay? All right. Next is going to be ln of a to the k is going to be k times ln of a. And again, right, if we're looking at ln, this is saying like e to the power of some j is equal to a, right? So that means that ln a is equal to ln of e to the j, right? But if you have this k floating around, what you're looking at is ln of a to the k is equal to ln of e to the j to the k. And remember, friends, we're not adding for this, okay? Exponent to exponent is multiply, all right? You need to know why that works. If you do not, that is okay. Go study it. You're gonna be fine, all right? Anyway, then you get ln of e to the jk, which is going to equal jk, but that's going to be the same as k ln e to the j, which is still going to be kj, which is equal to jk. The fourth rule we'll be looking at is ln e to the x is going to equal x. And that's going to make a lot of sense, right? We're saying e, because that's the base, to what power is e to the x? Surely it's x, right? And in that same vein, you can say ln e to some function, f of x, is going to equal to f of x, and you also get e to the ln of f of x is equal to f of x. Okay, again, like we mentioned, these are inverse functions, which is what we brought out up there. Do you remember that whole thing we said? Compositions of inverses equal x. Yeah, okay. Another things worth noting is that this holds technically for all log bases, so it could be log base 8 or whatever makes you happy. Asterisk, right? There are, of course, some constraints which we'll discuss in the next section. Okay. Another thing we want to cover is the general form. Okay. And so the way it will look is you're going to have, oops, let's do that in white. F of x is equal to a log b x minus h plus k. All right. Look, the reason why this is important is because as you've noticed with other functions, you can use these guys to help with the transformations of the function. Okay. Um, for this, it's not going to actually be the important part for our transformations. It's not going to be what we look at for our vertical and horizontal shifts. Okay. So let's get into it. A is going to be your vertical stretch. Okay. If you guys notice, the stuff on the outside, it always deals with the vertical business. Okay. Your K is going to be your vertical shift. Again, up K units, leave X alone. It's going to multiply output by K. C is going to be your horizontal stretch or shrink by a factor of 1 over K. Oops, sorry, 1 over C, my bad. And H is going to be your horizontal shift by H units. Okay, so if you have something like ln of x minus 7, right? Your H is going to be positive 7. And so your function will go from that, right? And it's going to shoot 7 units this way. So 1, 2, 3, 4, 5, 6, 7. Weep. Okay. As opposed to if you have it as negative, it'll go 7 units in that direction. So it'll go da 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 to like -7. All right. And that's